All right, as we're filing in, just have a look at this question on the slide and see if you can come up with a scheme for doing what the question's asking, right? So we have some coin that is biased. It comes up heads with probability P. We have low quality randomness essentially, and we want to get high quality randomness. We want a coin that is perfectly 50-50, producing random bits. So think about this for maybe another minute while more folks file in. How could we do that? Okay, let's get started. So does anybody have any ideas off the top of their head? Any ideas on how we could take a biased coin that comes up heads with probability P and like write an algorithm that takes these coin flips from this biased coin and turns them into perfectly uniform random coin flips? Is there anything that we could do to make that happen? Yeah. I see. So the idea is, for folks who didn't hear, the idea is kind of keep track of how many heads we've seen in a row and how many tails we've seen in a row. And when we've reached a certain number of these things in a row, we say, you know, something has happened, and that's when we start doing our algorithm, right? Something along those lines? Yeah, so that is not a bad idea. I like this idea of noticing that we're probably going to get some number of heads in a row, and we're probably going to get some number of tails in a row. And maybe we can leverage that somehow. I think one challenge with this particular idea is that we don't know P. We actually don't know the probability of heads. It's unknown, but we know that it is potentially not 50-50. So it's going to be tough to know how high to count if we don't know P. Yeah?
If we assume that like P is not exactly 0 or exactly 1, because then like it'll be impossible to get any.
Yeah, let's make that assumption. So P is not 0, P is not 1.
And then the second assumption being that coin flips are independent of each other, so like if it's heads before something.
Yep, coin flips are independent, sure.
Then like what you could do is like you take coin flips in pairs, and if you flip it twice, if it's 2 heads or 2 tails, you can throw it away and start again. But then like otherwise, if they're different, then you just say like it was heads if the first one was heads, and it's tails if it was the second one, or if like the second one was heads. So basically,
Gotcha.
because heads tails and tails heads are the exact same probability, because like it's just the same flip.
I think you've got the right idea. Let me sort of go through it piece by piece. So let me first make some room for myself on the slide. Yeah, so the idea was we're going to look at pairs of coin flips, okay? So pairs of coin flips can come up a number of different ways. They can come up heads, heads. They can come up heads, tails, tails, heads, or tails, tails, right? Well, what's the probability of heads, heads? P squared. P squared. What's the probability of heads, tails? P times 1 minus P, okay. Tails, heads, that'll be 1 minus P times P, which obviously is the same thing, okay. And tails, tails is 1 minus P squared. Okay, so what do we notice? We want 2 outcomes that have the same probability. So we can look at the 2 middle outcomes here, these 2, and we can sort of treat those as the 2 things that we're looking for, right? So we want to take this coin that comes up heads with probability p, and we want to create an algorithm that allows us to produce outcomes with equal probabilities. And here are two things that have equal probabilities. So we're almost there. So what we could do is we could say, we have an algorithm, and it's going to remap anytime we see ht to 0. That's this 0 up here. And anytime we see th, we're going to map that to 1. And then we have to do one more thing, which is take this outcome and just say sort of re-roll. Start again. Resample. Does that make sense? Do folks see what this is going to do? We have two outcomes. One comes up heads, tails with probability p1 minus p, and one comes up tails, heads with probability p1 minus p. These are equal probabilities, and whenever we get a heads, heads, or a tails, tails, we just throw it away and try again. Yes? This part on the right? Yeah, so this is saying we're going to, anytime we see ht, anytime we see heads, tails, we're just going to call that a 0. Okay? Anytime we see tails, heads, we're going to call that a 1. Right? Because our goal is to produce zeros and ones with equal probability. We don't need to have them be associated with the coin flip outcomes. So normally we might say like heads is 1, tails is 0, or something like that. We don't need to have this, such a strong connection between the outcomes of the coin and the outcomes of the algorithm. The algorithm can relabel these sort of outcomes as it wants. So that's what we're doing here. We just have a different labeling scheme. When we see this pair heads, tails, we call it a 0. Tails, heads, we call it a 1. Okay? So that's one thing that we could do. And this is sort of like this is an answer that comes from von Neumann. If you've heard of him, he's like the guy who invented the modern computer architecture, like everything inside of our computers, our phones, etc. Like, that's due to him. But he also came up with this thing, which is kind of fun. You can flip a coin twice, and you can label them this way, and each one will have this probability, and that gets you a fair coin, even if you didn't have one. Okay, so there are other alternatives, right? This is not necessarily the only answer. But this kind of captures the idea of taking low-quality randomness, where we have this coin that's biased, we have this probability p, we don't know what it is even, and turning that into high-quality randomness, like the kind that gives us half-half probabilities. So we have a distribution that's not what we want. How do we convert that into a distribution that is what we want? And that's what we're going to talk about in today's lecture. Questions so far? Okay, let's go. So last time we talked about doing exact inference with our Bayes nets. We have a big probability model. We're going to concisely represent it as a Bayes net. We're going to ask it questions. We're going to fill in some evidence and query it with whatever we want to know. And last time we showed the process for doing exact inference in Bayes nets and how we could do either inference by enumeration, or we could do variable elimination, where we're summing out variables as we go. And we said, okay, this is all well and good, but in the worst case, we saw that it was going to be NP hard, it was going to be it was going to be count P hard or sharp P hard. And so this is saying it's going to blow up in the worst case. It's going to be exponentially hard to do exact inference. So maybe we can do approximate inference, and it will take us less time and less memory. That's the main idea. Okay, so before we get into what sampling is, why would we want to sample? Well, it can be very fast. So instead of worrying about this exponential blow up and having lots and lots of conditional probability tables in memory, and these things could grow potentially exponentially sized, this sampling procedure could be a lot faster. It could be a lot more memory efficient. Usually requires very, very little memory. And these algorithms will end up being quite simple. So that's the sort of why question. And the basic idea is we're going to draw samples from what's called a sampling distribution. And the hope is that our sampling distribution will be equal to the true probability distribution P that we wanted to sample from. And so we're going to consider different algorithms that can do this kind of drawing from a distribution in order to make sure that we get the distribution that we want. Right? So how can we ensure that our outcome of this algorithm gives us a fair coin instead of a weighted coin or something like that? Okay, so here's another example. Imagine that we have two agents, A and B, and they're playing Monopoly. Who has played Monopoly, by the way? Okay, a lot of people have. Who has not played Monopoly? Okay, some people have not. So if you haven't played Monopoly, this works for other games too. So just fill it in with your own favorite game, as long as it works for two players. So let's say we have two agents. We want to know, for these two agent programs, what's the probability that A wins? Okay, what's the probability that A beats B at Monopoly? Okay, so we could just compute this. Like, if we have the two programs, and we knew kind of, if we were sort of omniscient and we knew how all of the random die rolls and all of the sort of card drawing was going to work, we could sort of bake that into our calculations, and we could compute this in closed form. So that's going to be like method one, which might be a kind of a dumb approach. But let's let S be a sequence of all the random stuff that's going to happen in this Monopoly game. We're just going to pre-compute all the randomness. So anytime someone needs to draw a card, anytime someone needs to roll the dice, I don't remember what else happens in Monopoly. Like anything that happens in Monopoly that's random, could even be randomness within the programs. If there's a random choice in the programs, we're going to pre-compute all the random outcomes in advance in the sequence S. Then given S, the outcome of the game, the value of the game, the value for a particular sequence is determined. It's completely determined, right? We have all the randomness, we pre-computed it, and so anytime we need randomness, we just look at our sequence and we pull another random outcome out of our sequence, and then we apply that, whatever the result is, to the game. So we could do this. Yeah?
When you say a sequence, does it mean you consider for a roll of 1, 2, 3, 4, 5, 6, or like if it goes on this house, how much you patient calculus all of it?
Yeah, so a sequence here means each item in the sequence is like, I rolled the dice and it came up 6. Or, I drew a card and it was this particular card. So we just pre-compute all of the randomness and just say like, anything that's random that happens in this game, I know that the first die roll is going to be a 6, and I know that the first card draw is going to be the 7 of clubs. I mean, that's not Monopoly, but like, you get the idea, right? Okay, so does it make sense? All right, other questions? Yeah? Are we ignoring things like trading? So so we can include trading. This would be like part of the agent program. So if the agent program is deterministic, it's included by default. And if the agent program makes trades randomly or something like that, then we fold the randomness that's governing their trading behavior into the sequence. So this still works. Yeah, thanks for that question. Other questions? Okay, so let's try and figure out what would be the probability that A wins. Well, this is easy. We can just look at all the possible random sequences, sum up the probability of that random sequence, and multiply by the value of that sequence. So did they win? So we're just looking at all possible random sequences, and then we're adding up the value of that sequence, and this will give us sort of our win rate. Any problems with this? Yeah, there's a lot of states. There's a lot of sequences, right? There's a lot of sequences in this summation. How many sequences? There's infinite, actually, yeah. So that's kind of a big summation. There are infinitely many sequences because I don't know about other games, but Monopoly actually can go on forever, and sometimes it feels like that. Right, so we don't want to have to do this infinite summation. Can we get by with doing a finite summation? Maybe. I mean, it could be approximate, but if we just look at n different sequences, and then we compute the value for n different games, maybe n is like 100 games, we have these two agent programs play each other, we pre-compute all the randomness, and then we multiply this P of S times V, or rather, so what we were doing before is we multiply p of s times v and sum over all the s's. Here, we're just going to say 1 over n times the sum of all the v's. So this is saying, like, what's the average in this sample? So we're not going to look at every single sequence anymore. We're going to look at some subset. This is going to be like our 100 games. And just we're going to measure the fraction of wins in that particular sample. So this will be a lot quicker. We don't have to sum over an infinite number of sequences. It might be less accurate, but hopefully if the number of games is big enough and the agent's performance is different enough, then we'll be able to detect who's going to win more. The concept makes sense? Okay, great. Yeah, and so like we could, I mean, maybe if their performance is close together, we might need more games. But if their performance is so close together that we need like, I don't know, 10,000 games, then it kind of doesn't matter which one of them is better. We can just say they tie. Okay, so we're not going to need that many games, hopefully. All right. We're going to work our way up to more complicated types of sampling, but the main thing that we're going to need to be able to sample from is a categorical distribution, because we're going to keep things discrete here. We could do this with continuous distributions as well, but let's keep things discrete. We'll have categorical distributions. Think of this as, I don't know what you prefer, like an n-sided coin or like an n-sided die, or whatever makes more sense to you. But we're going to simulate this outcome thing that has d possible outcomes. And in this particular game, instead of having a coin that we flip with probability p, it comes up heads, now we're going to say that the sort of unhelpful or the low quality randomness that we start with is just a uniform distribution from 0 to 1. This is like the classic thing that you get from Python. So how are we going to convert this uniform random distribution into a sample of a categorical distribution like this one here, right? So if red comes up with probability 6, let's say we have this color variable, red is 0.6, green is 0.1, and blue is 0.3. How can we convert this uniform random number into a categorical distribution? Any ideas here? Yeah.
You can think about like changing the number line from 0 to 1, where like 0.6 is red, 0.1 is blue, 0.3 is blue, and like except for the edge cases.
Yeah.
Whenever you got the random number generated, it'll lie in one of the two segments of this picture.
Great. So the thought was paint the number line, red, green, and blue, and the length of the paint is going to be proportional to the probability of the particular outcome. So does everyone see why this might work? It's sometimes helpful to visualize it like this. So what we're saying is we have a uniform random number. It starts at 0, it goes up to 1. And essentially what we're saying is when we have a uniform distribution, it's almost like rain is falling on this number line, right? And when a raindrop hits this number line, it's somewhere between 0 and 1. But we want that to correspond to an outcome. And so this amounts to essentially thresholding. We're saying if I get a number that's in this range, it counts as red. In this range, it counts as green. And as long as the raindrops are uniformly distributed, then we'll get the outcomes with the associated probabilities that we want, right? So we essentially write down these thresholds. Our algorithm says, draw a uniform random number from 0 to 1. If it's less than 0.6, call it red. If it's between 0.6 and 0.7, call it green. And if it's not, call it blue. Okay? Does that make sense? Questions before we move on? Yeah.
Define discrete categorical distribution again.
Right. So what is a discrete categorical distribution? So discrete distribution and categorical distribution are two different names for the same thing. It just means that there is a discrete set of outcomes. So I can count the outcomes. And like there are this many categories that things can fall into. So here we have 3 categories. Make sense? Great. Other questions? Okay, great. So if random, this is like Python's random function, returns 0.83, that's somewhere like in this region, and so we would call that a blue, right? It's above 0.7 So our threshold would say, yeah, we'll call that blue. And after sampling this 8 times, we might get these samples, and so we would get a bunch of different shapes. Some of them are red, some of them are blue, some of them are green, okay? All right, so we're going to use this mechanism in our Bayes nets, and we're going to sort of work our way up from simple algorithms to complicated algorithms, and we're going to try and take low-quality randomness and turn it into high-quality randomness. Okay, that's the game. So first we'll start with prior sampling. We'll get into rejection sampling. These are the 4 different types of sampling we're going to talk about. Prior sampling is first. And so if you imagine that we have a Bayes net that has just 2 variables in it. One is shape, okay, and one is color. You can imagine, you can sort of visualize that. Our artist drew this picture where shapes come down through this little machine thing here. Shapes land on this conveyor belt. They sort of get sprayed by this thing with some conditional probabilities. So if it's a triangle shape, then like this thing sprays it with these probabilities. If it's a circle shape, then it sprays it with those probabilities. Then they move down the line, and this thing just sorts them into various bins, right? So according to which color and which shape they are. That's kind of the big picture of what's going to happen here. So prior sampling essentially says, let's look at our Bayes net and just do like the most intuitive thing. If you were going to sample from this Bayes net, and you want to get samples from the joint distribution that this Bayes net represents, well, where should we start? I mean, the best place to start is the one that has no conditioning variables. So we'll just like draw a random cloudy, or I guess I should talk about the Bayes net. So imagine that we have this 4-node Bayes net, and we want to figure, we look out the window and we see that our neighbor's grass is wet. And we want to figure out whether it's wet because they turned on the sprinkler that day, or it's wet because it was raining out. And both of these things might be influenced by whether it was cloudy in the morning. Because if it was cloudy in the morning, then maybe they think it's going to rain, and so they don't turn the sprinkler on. And if it's cloudy in the morning, it's actually likely to rain. So both of these things kind of depend on the cloudy variable. And so we might want to ask, like, what's the probability of a particular like pair of or tuple of cloudy, sprinkler, rain, and wet grass, right? So we sample cloudy because it doesn't have any parents. It's pretty easy to sample from. And let's say we get a true. For this lecture, I'll say that true is blue because that kind of rhymes, and then red will be false. So we sample cloudy, we get a true. Then we want to sample sprinkler, or we want to sample rain. We'll just start with sprinkler. Sprinkler has this conditional probability table, and we're going to condition on the cloudy that we just got. So we're looking at the top 2 rows. And we sample from this, and maybe we get a false, right? So sprinkler was off. Then we move over to rain, and then we sample from that. Again, we had cloudy before, so we look at these rows. And then we sample from that. Maybe we get a true. And now we have rain and we have sprinkler, so we can look at this last conditional probability table. We look at these rows, and then we sample again, and maybe we get a true, okay? So our sample looks like this. All right, so we could keep doing this. We could sample again, maybe we get this, etc. What is the probability under this sampling procedure? We'll call this is our sampling distribution. So if we do this procedure, which is called prior sampling, what comes out? What are the probabilities of these different outcomes? Well, to get here, all we did was look at the corresponding rows of the conditional probability tables. So we can write this as essentially the probability of cloudy times the probability of not sprinkler given cloudy times the probability of rain given cloudy times, I don't know if I have enough room here, times the probability of wet grass given not sprinkler and rain. So this should look kind of familiar because this is just a product of conditional probabilities that are dependent on the parents in the Bayes net structure. So that's actually like the joint distribution of this Bayes net. And we're just looking at the particular outcome that we got. Okay, so more on that in a second. What's going on here is for each sample, each shape that comes down this conveyor belt, we're going to look at the Bayes-Net structure in our topological order, so parents first, then leaf nodes later. And for each node in the Bayes-Net, we're going to sample that node according to its conditional probability distribution. And then at the end, we'll have all the nodes sampled, and then we can just return the values that we got for all the nodes. So this process will generate some samples, and what are the probabilities associated with those samples? That would be the sampling probabilities, S. So for a given sequence, or sorry, for a given set of variables, this sampling distribution looks like this. It's the product of the conditional probabilities. And because this is sharing the same structure as the Bayes-Net, we already know that this is equal to the joint distribution over those same variables. So this is saying that our sampling distribution matches our joint distribution. That's a nice property to have. Okay. So we have samples, but we want probabilities, right? So we have like examples of outcomes that could come from this process, but we want to know what was the process that generated those samples. So this is not like, we don't just want to have these shapes in our baskets. We want to know what's the probability of shapes going into this particular basket, right? And how we're going to do that is we're going to imagine that we have n samples, right, that are drawn from this sampling procedure. And then from those n samples, same as before, we're going to estimate by sort of summing up and dividing by the total number of samples how many samples we got for each bin. Okay? So when we see a particular outcome, we just count it, and then we see what the total count was, and then we figure out that the probability for each basket in this picture, is just the count of how many shapes of that color went into that basket divided by the total number in all the baskets. Okay? So that's the idea. So if we let n go to infinity, then by the law of large numbers, this thing converges to the sampling distribution. And the sampling distribution we already showed is the same as the joint distribution. So essentially, we have this estimate Q. Q is an estimate of the sampling probabilities that we produce using n different samples. And it turns out that when n is really big, that number, that estimate Q, converges to the real probabilities from our joint distribution. This is a very good property, and it means that the sampling procedure is what we call consistent. So this consistent is different from the consistent when we talked about heuristics. This is like a separate notion of consistency. This one says that if I let the process continue for a long, long time, if I let n go to infinity, then this sampling procedure converges to the thing that I want it to converge to, which is the joint distribution. Okay? So that's prior sampling. Let's look at an example. So we're going to get a bunch of samples from the Bayes-Net. They might look like this. And we want to know the probability of wet grass. Okay? Oh, for some reason, I was going to try and build this slide. Okay, yeah, so here we'll build it one piece at a time. So we want to know the probability of wet grass. So we can look at the wet grass variable here and just count how many times we got wet grass and how many total samples did we get. So we got wet grass 4 out of 5 times. We got not wet grass 1 out of 5 times. So that's the not wet. Okay? So if we want to know the probability of wet grass, we have these counts 4 and 1. We just normalize them to get these probabilities. And this will get closer to the true distribution with more samples. But so now we have like 0.8 wet and 0.2 dry. What if we want to know the probability of wet grass given that it was not raining? Is it still 1 over 5? Well, we have all these samples. Can the samples maybe tell us about this question? Yeah. So how did you get 100%? If you only look at the non-rainy ones, which are the ones that are consistent with our evidence here, right? We have this evidence, and so we say only look at the non-rainy ones. We only have this one sample. And so you're saying, well, 1 divided by 1, that seems like 100%. So yeah, so this is true, that this would estimate that we would sort of have to throw out a bunch of samples. And so throwing out a bunch of samples is basically going to be the next algorithm. It's called rejection sampling. It's going to say, when we see stuff that's not consistent with evidence, we throw it out. So it's a simple application of prior sampling, the thing we just looked at, for estimating conditional probabilities. So let's say we want the probability of, we're going to flip it around. We want the probability of cloudy given rainy and wet grass. Well, we know by sort of the laws of conditional probability that this is proportional to the joint distribution over those 3 variables. The constant of proportionality, just as a refresher, is the probability that it's raining and wet grass. And then for these counts, we're going to basically have samples with not rainy and samples with not wet, and none of that is relevant to figuring out what we want these counts to be, right? So we do our same prior sampling process, and anytime we get something that's inconsistent with our evidence, we're going to throw it out and just sample again. So the counts are only the counts for the samples that match the evidence, and then we're just going to reject all the other samples. So that's why it's called rejection sampling. So this also turns out to be consistent. It'll get you the right conditional probabilities in the limit. So that's also nice. And how does it look? Well, imagine we get this sample, okay? And we want to get the probability of cloudy given rainy and wet grass. Well, this sample is consistent with rainy and wet grass, so we can keep it. No problem. Let's generate another sample. So we generate the sample, and we run this whole prior sampling thing. So we sample C, then we sample S conditioned on C, then we sample R conditioned on C. And when we sample R conditioned on C, if R is not consistent with our evidence, we can actually stop. We stop early. We don't need to keep running through this prior sampling process for nodes after we find a node that's not consistent with our evidence. So we can stop here, we can cross the sample out, throw it in the garbage, and then we move on to our next sample. So maybe our next sample looks like this. We get all the way to the W before we have to throw it out. So we throw that one out too. We get another one of these. We can throw that out early. And then we get this one. Okay, so we've attempted to sample 5 times. 3 times we got all the way to the end before we had to throw something out. And then 2 times we got to stop early, which is a little bit faster. And so the procedure looks kind of like this. So for each potential sample, we're going to have some evidence. It's the same evidence for all the samples. We're going to go through in the topological order the same as before. We have our Bayesnet. We're going to sample each xi from its conditional distribution. And if it's not consistent with the evidence, we just reject it, okay? We return. Or you could imagine that, like, if we're sampling a few times, then like we could have like for j equals 1 to n, okay? So like there could be capital N. There could be like this outer loop where we're sampling more times, and so return would just be like continue this outer loop. But yeah, so every time we see something not consistent with the evidence, we throw it out. All right. So we all like car insurance. We keep coming back to this car insurance example. Everybody loves car insurance. So if you do this for the car insurance network, and you want to estimate, based on all these blue things, what's the property cost, you can show that rejection sampling allows you to do that, and that the error goes from some big number to some small number as you get more samples. So overall, that's kind of nice. That's good. But look at this number here. That's actually quite a big number. And look at this number here. This is like, so we're saying that after 1 million samples, we're still at like 0.01, which might not sound that bad, but usually we're used to these sorts of like central limit theorem law of large numbers things converging at 1 over the square root of n. And n here would be like 1,000,000. So we would actually expect this thing to be like 1 over 1,000, which means that our error is about 10 times larger than we think it might need to be. So the reason this is taking a lot of samples to converge is that we have a lot of evidence variables, and we have to throw stuff out every time it's inconsistent with any of our evidence variables. So the more evidence variables you have, the more likely you are to reject your sample and throw it out and have to resample. So when there's lots and lots of evidence variables, you end up throwing out lots and lots of samples, and it ends up taking lots and lots of time. Okay, questions on prior sampling or rejection sampling? Again, the idea is we're just taking low quality randomness and turning it into high quality randomness. We want to try and sample from this Bayes net to answer our questions. Okay? The next one is going to try and fix this problem of like, why are we throwing out so many samples? Why are we spending so much compute on samples that are like not consistent with our evidence? So the idea with likelihood weighting is rather than having this thing just sample from the original distribution, we know that we want to sample from, let's say that we want to sample blue shapes, right? We want to sample from the distribution of like shapes conditioned on the color being blue. Well, why would we waste our time with other colors, right? We need them to be blue in order for us to keep the samples. So we're just going to color everything blue. Obviously, if this was a conditional distribution originally, if we were like coloring different shapes with different probabilities, then this is no longer going to be the same distribution. But it is a distribution that has only blue shapes, and so maybe we can kind of fix it after the fact. Right, so the problem with rejection sampling was that if evidence was unlikely, then we were going to reject lots of samples. And in some sense, the evidence was not exploited during the sampling process, right? So we would have all these different shapes. If we care about like blue shapes and we're sampling with rejection sampling, then we have to throw out all these red shapes, we have to throw out all these green shapes, and that's not great. We're not happy about that, right? So if here's our example, right? Shape determines the color, and then we want to sample the shape conditioned on color being blue. We have to throw out all these other shapes. That looks like this. We get a small number of samples we can actually use. The idea here with likelihood weighting is we're going to fix the evidence variables, meaning set them to be the thing that we care about, blue, and then we're just going to sample the rest of the variables. But we said this already, the sampling distribution is no longer the same distribution because we've like put our thumbs on the scale and now we're getting all blues. Oops, all blues. So the solution is we're going to reweight the samples according to how likely they were. So we're going to basically find a way of compensating for the fact that we've put our thumb on the scale by like rebalancing the scale so that when we sample from this new distribution, we can reweight the results and still sort of in a weighted sense. Imagine we're throwing all these shapes that are these different, now they're one color, into these same bins, but before we throw them in the bin, we just make some of those shapes heavier. I guess that's like why we're making them bigger. So if we throw them in the bins and we make them heavier before we throw them in, then all we have to do is instead of adding up the count of the shapes in these bins, we're going to add up the total weight of each bin. So here, this is the Bayes net. We're basically saying that the color has been fixed to blue, and we're still going to be thinking about this. We sample the same way as before, but now all the colors are blue because we're just coloring everything blue. And this is not the distribution that we would like it to be, but we'd like to fix that with some weighting. So let's look at this example again. Now we're going to say that the sprinkler and the wet grass variables have both been set to true. That's indicated like this. The slash marks mean that's evidence. Okay, and then we're going to do the same process as before on all of the nodes that are not colored in yet. So same process as prior sampling. We start with cloudy, we take a sample of cloudy, we get a true. Then we have to pick rain or sprinkler. Let's say we pick sprinkler first. When we pick sprinkler, we notice that the variable's already set, so there's nothing to sample. But we notice also, if we look at this conditional probability table, that this particular value, true, is a little bit unlikely, right? So our conditional probability table says condition on cloudy being true, sprinkler is only true with probability 0.1. So when we're writing down our samples, we have like S and W, which are sort of determined already. We've sampled cloudy, and then we want to go and sample sprinkler, but sprinkler's already sampled. So what we want to do is, instead of like giving this like unit weight, like just we don't care what the weight is, it's like 1, we're going to multiply that by the probability in this table that is associated with the outcome that we've sort of locked in already. So cloudy is true, sprinkler is true. Let's multiply this weight by 0.1 and say we're going to downweight this. It doesn't look like a typical example. Let's give it less weight than we would otherwise give it, right? So the weight comes directly from here. It's saying when you see an evidence variable, instead of sampling it, you're just going to look in the table and decide how much to downweight it. Yes?
How do we know what the conditional probabilities are going to be for the evidence given its parents? If we're doing the sampling for the whole net, how do we know the evidence has like the conditional probability of 0.1?
How do we know what the conditional probability is for the evidence given its parents? Well, in this case, sprinkler, we have a Bayes net, which means we have the structure, but we also have the conditional probability tables, right? So if we see evidence conditioned on stuff we've sampled already, we just look at the table, right? So we have this table already, and we have evidence here conditioned on parents. So if we've sampled cloudy, we're good to go. Is the question whether, if we get an evidence at the top node, what do we do?
I guess I was wondering, if we're trying to like approximate the probabilities, then how do we, if we don't know like the conditional probability table, do we have to approximate that too?
I see. So the question is, if we don't know the conditional probability tables, what do we do? Well, I guess in the sense that like we're starting with a Bayes net, we're assuming that we have the conditional probability tables. But yeah, I mean, where does the Bayes net come from? Now we have to put our modeling hats back on and say like, let's try and model the world, come up with these distributions, and yeah, that's a different problem. Yeah. Other questions? Yes?
Could we just run this sampling procedure to estimate the probability of the sprinkler, and then use the sample, like the data we just sampled, to estimate the probability of wet grass with like the conditional probability table we just sampled?
So the question is whether we can use this procedure to estimate the probabilities in the table?
Yeah.
So I'm not sure how you would run this procedure if you didn't have the tables, because you're sampling cloudy, you need to know the table for cloudy to know that it's 50-50. When you get to rain, you need to know the table for rain given cloudy so that you can see that it's 0.8, 0.2. So I'm not sure how, that it feels like a little circular to me. But there are other ways that you can like construct a Bayes net from the world, but that's like sort of a different topic. That's like we would have to put our modeling hats on. Okay. If that's not a satisfying answer, we can chat about it more after class. Okay, so we've done cloudy, we've done sprinkler. We know that wet grass is also sort of set for us, but we haven't got to wet grass yet. We've done cloudy, sprinkler, and now we have to sort of do rain. So we look at the rain table. Rain hasn't been sampled yet, and it hasn't been set by the evidence. So we do the same sort of normal prior sampling thing, and we just look at the conditional probability tables condition on cloudy. We look up 0.8, 0.2, we sample from this, and let's say we get a true again, okay? So now rain has been sampled. And anytime we sample a node in here, we don't adjust the weights, right? Because we would sample according to those probabilities, and we've already sort of factored them into our calculation. But when we get down to wet grass, we see that we can't sample wet grass either, right? We've already sort of set this one with our evidence variables. So we do the same thing as before. We look in the table when we get to the wet grass, and we say, all right, it needs to be consistent with the evidence, which is that sprinkler is true, rain is true. And so if we see that wet grass is true, which is what the evidence tells us, then we see that that's likely with 0.99 probability, which says, yeah, actually conditioned on all the stuff we saw already, stuff that we sampled and evidence that we have, this particular value of wet grass is pretty likely. It's 0.99 out of 100. So we multiply by 0.99, which means we don't really downweight the sample any further. It was unlikely that we would have seen sprinkler be true, but given that we saw that, this is all totally fine. So as we go through this thing, every time we encounter an evidence variable, we look up its weight in the tables, and then we downweight it according to how unlikely it was. Let's put that into code. We start with some evidence, and we start with a weight for our particular sample that's set to 1. And then for each node in the topological ordering, we go through our BaseNet, we do our whole BaseNet thing. If xi is an evidence variable, then we have to do this new step, which is to look up the table, set x to the observed value, this is the evidence value, and then set the weight according to the probability of seeing that particular x given the parents in the table, and then multiply the sort of aggregated weight by this new probability. Otherwise, we just sample the same way as before. Okay? And then, we get to the end, we have all the variables that have either been sampled or they were set by the evidence. We also have a weight associated with that sample. So this is saying we have a sample and we know how much weight to give it. Okay. So when we get to the end, we're going to take all of these samples, we're going to weight them by the appropriate amounts, and then we're going to get the weighted sum rather than the normal sum. So if our sampling distribution splits things into the hidden variables z and these would be the sampled variables and the evidence variables e, which will be the fixed variables, then the sampling distribution doesn't have to look at any of the evidence stuff because that's all fixed for us already. So all we're doing is we're multiplying by the product of all the non-evidence variables, these z's. Right? So this is just multiply the conditional probabilities in the BaseNet for all the non-evidence variables. That's the sampling distribution. But each one of these samples is going to have a weight associated with it. So each z-e pair, where z, these are bold-faced vectors because z is all the non-evidence variables and e are all the evidence variables. So this is the weight. This is the combined all of the variables in the network. And that's going to have some distribution over these outcomes. But each one is going to have a weight. And what's the weight? Well, the weight, we only adjusted the weight when we saw an evidence variable that was already determined, so we looked it up in the table. So when we see an evidence variable, we multiply the conditional probability tables for the evidence conditioned on the parents of the evidence. And then we're just going to smush these two things together. When we get a sample, we multiply that by the weight. So when we do these two things together, we have our sample, we multiply that by the weight for the same ZE combination. And this is going to look like multiplying the product of the parents of the Z's with the product of the parents of the E's. But Z's and E's, that's just all the variables. So essentially, this is the joint distribution again. So likelihood weighting is consistent, and we've just sort of proved that to ourselves, right? We're getting the joint distribution back, and that's good. So this turns out to be an example of a broader class of techniques called importance sampling, and we could have started here, but I think it's more intuitive this way. Importance sampling basically says, I have some distribution P that I'm trying to get quality estimates of this distribution based on samples, but it's hard to sample from P. So instead I'm going to sample from some other distribution called Q. Who knows what Q is? We don't know. It's just anything besides P, really. There are a couple of technical constraints on what Q is allowed to be, but essentially we have some other distribution that we know we can sample from, and we would like to sample from that because we can't sample from P. Well, if we sample from Q, we're going to get samples of Q, not samples of P. So we're just going to, again, put our thumb on the scale and say, when I get a sample from Q, I'm going to reweight it according to whatever I need in order to get samples from P out. And the simple thing that you can do is reweight it by p divided by q. And you might think, okay, well, does this really solve the problem? Like we didn't know how to do anything with p before, but p appears in this reweighting scheme. So are we're just delaying the inevitable here? And it turns out, actually, no. Like, estimating the ratio of these two distributions can be easy, even when sampling from p itself is hard. So you can estimate this ratio, and we just did it. So if you don't believe me, like, we just did this. So the example here is saying, like, we're going to sample from this distribution, S, which is essentially our Q, and then we're going to reweight by this thing, which is essentially our P divided by Q. And the result is that we're going to be sampling from P, even though we didn't get to sample from P. So this works. It's a class of algorithms called importance sampling, and we're basically adjusting the importance of the samples so that we get the right distribution. Okay, let's go back to insurance, because we love insurance so much. We looked at this before. We said, all right, rejection sampling goes down to this value. Maybe that's not so good. It's not converging as fast as we would like. Turns out that if you stop throwing away all the samples and you just do likelihood weighting, then you can get this error down to the same value as it hit at about 1 million steps after only like 1,000 steps. So it's like way faster. This is like the use case for likelihood sampling. Yes, question? Yeah, that's a good question. So this is the error in our estimate of the probability distribution for the property cost conditioned on that evidence. So there's a couple of steps. One is we do the sampling procedure. We throw all the results into bins, and then we look at the counts. And in this case, we're looking at the weighted counts. So that gives us our estimate. And then when we have our estimate, we say, how close is that estimate to the true distribution? Other questions? Okay, great. So likelihood weighting is good. It is much nicer that we don't have to throw samples away, right? In rejection sampling, we ended up throwing a lot of samples away. Now we can use all the samples. And it has this property that, like, when we condition on evidence, if that evidence is like up here in this Bayes net, then as we sort of step through these calculations and we sample subsequent nodes, these purple nodes don't depend on the evidence, but many of the nodes that are sort of further down in the chain do depend on the evidence. And so if we were conditioning on, let's say we're conditioning on these 4 nodes, like the red ones have no parents and the yellow one is somewhere in the middle, then like as we step through this sampling procedure, purple nodes are not dependent on any of our evidence. They're not influenced by the evidence. But all the stuff that's red is influenced by the evidence. And then when we get down here, we have one that's influenced by like internal nodes and sort of top nodes, so like the orange ones as well. So all the red and orange nodes in this graph are influenced by the evidence. So much more of the sampling procedure is taking the evidence into account. Just sort of like a graphical way to think about that. But if we had evidence down here, then this would not work, right? We don't have any way of sort of filtering that evidence back upwards through the Bayes net. And so we would not be able to adjust the sampling procedure to account for that kind of evidence. So likelihood weighting still has some weaknesses. And if this kind of thing happens, it'll be one of the weaknesses of likelihood weighting. If we have evidence in k different leaf nodes, and let's just say those leaf nodes are binary, the weights that we will multiply together are proportional to basically 2 to the minus k, so 1 over 2 to the k that we would see that particular evidence that we wanted when we finally get down to these leaf nodes. And that means that it's going to be highly unlikely that we see the evidence we were looking for, and it's going to be much more likely that we just see a bunch of stuff that we can't really use. So it's not like rejection sampling. We're not going to throw those samples out, but we're going to crank the weight down on those samples by quite a bit. And when we do this, there's going to be some samples that just get really lucky and have high weight, and most of the samples are going to be sort of your average samples, and they'll have really low weight. And as a result, we're going to sort of see the same picture that we saw a while ago, where we were trying to estimate. Let me go back to this example, right, where I said, what if we wanted to know P of W given R, and we only had one sample we could use? It's essentially like this. We're saying that there's one highly weighted sample now, and most of the rest are very low weighted. Right, so ideally we would like each variable to see all the evidence so that this doesn't happen. All right, so while you're putting in your attendance codes for today, think about this. If I'm someone who just wakes up in the morning and I wake up in some city, it could be Atlanta, it could be Boston, it could be Chicago. Imagine that I'm someone who just wakes up in a random city and then decides to go to another random city that same day. I do this every day, and then what we want to know is, after an infinite number of days, which cities am I likely to be in? And there's two scenarios. One scenario says that there's exactly one flight between each of the cities, and then the other scenario says, actually, between Boston and Chicago, we've added another flight. So we can get between Boston and Chicago two ways, right? And I just pick my flight uniformly at random also. So I pick the flight that can take me to any of the cities that are in this graph, and I pick uniformly at random between the three flights or the two flights. Okay, so the question is, in the infinite limit, what fraction of the time do I spend at each node? And we can start with this simpler graph on the left. What do people think? Yeah? All the nodes are 1/3. Yeah, sort of symmetry argument, right? Like, if we're looking at the infinite limit, there's a half probability that I go from each one to each one. There's an equal probability that I go back. All these things are going to equal out in the limit. What about the other case, though? What about this case? I mean, okay, we can make the same symmetry argument for B and C. We think B and C, maybe Boston and Chicago have the same probability. But like, what about A? Is it greater or less? B and C would be greater? Folks agree with that? Raise your hand if you agree. Okay. Why do you think it would be greater?
I feel like it's like the game show we had in CS78. There were 3 doors, you open one, then the probability of the ghost being behind the other door would be greater.
Yeah, like the Monty Hall problem. Yeah, so I mean, when there's more doors, when there's more flights between these cities, it feels like there's more probability that that's where you'll end up. So it has something to do with the degree of the nodes in the graph. Let me make some more space for myself here. So here's what we could do. We want to know the long-term behavior, right? When this thing has converged to some final distribution. And let's think about like what the transition probabilities are in this graph. Let's say, I want to know the probability that I'll end up in Chicago on the next time step, conditioned on like where I am in the network right now, which is probably A or B, because you can't get to C from itself. So the probability of C prime, which is the probability of getting to Chicago, is the probability that I start in Atlanta and then take a flight to get to Chicago, plus the probability that I start in Boston and take a flight that gets to Chicago. So that's this. What else can we do? Well, we know that this is the long-term behavior, right? So this is like in the limit where like the distribution is not changing over time. Everything is settled. These distributions have like reached their steady state. So we know that this is just equal to whatever the last probability of being in Chicago was. So we set this whole thing equal to P of C. Okay. So I might have to make some more room for myself here. Let's see if I can just write smaller. So we also know by symmetry that whatever this is equal to P of B. And then we can sort of like start adding terms back in here, right? So what is the probability of getting to C, getting to Chicago from Boston? Well, that means we're in Boston, and we take a uniform distribution over these three actions. So 2/3 of the time we end up in Chicago. So P of C given B is 2/3. And for A, if we're in A, I'll draw it in another color. Suppose we're in A, right? We might go to Chicago, or we might go to Boston. So 1/2 is the probability of getting to Chicago from Atlanta. Okay? So, and now we know that P of B, which we had here, is equal to P of C. So we can do a lot of things here. We said P of C prime equals P of C. I'll do that. I'll still do this in blue. So P of C, right? C prime equals C, because we're at the sort of steady state behavior. P of C equals P of A over 2. That's this 1/2. Times, plus P of B, which is this part. But I'm going to write that, because we have this piece, as P of C. And then we multiply that by 2/3. Okay, and so if you simplify this, you end up with like P of C divided by 3 equals P of A divided by 2. And essentially we get P of C equals P of A times 3/2. So that says P of C is 3/2 as likely, 50% more likely than P of A. So this is saying, like, I can estimate the probability that I'm going to be in a particular city in the very long term when n goes to infinity by imagining the sort of steady state behavior of how these sort of transitions between cities evolve. And steady state means that I can set the probability of C equal to the probability of C prime. Symmetry lets me set C equal to B, and then I fill things in according to my uniform distribution over the number of edges on each node. So this idea of just, sort of walk around this graph randomly. I wake up in a city, I move to another city. I wake up in that city, I move to another city. Keep doing this process, and eventually we can converge to some steady state behavior, and we can calculate what that steady state behavior is. And it might be an interesting probability. Okay? Yes?
What's the difference between PC and P plus C prime?
So one is sort of like, so C prime is like the next step probability. So it says like, given my current time step, what's the probability that I get to C on the next time step? And then C is just the probability that I'm in C right now. So in the long term, these things are actually equal to each other, because that's what the definition of sort of like having settled means. It says the probability of C doesn't change over time anymore. So that's what allows us to set those equal. Yes?
So how were you able to do like P of C equals P of A over 2 plus 2/3 P of C? I don't understand that line.
How were we able to do this part?
Yeah.
Yeah, so I skipped one step because I was running out of space. But you could think of this as P of B. So we were here, we said P of A times P of C prime given A. We looked at this, we said if we're in A, there's a 1/2 chance of getting to C, so that's a 1/2. So the second piece is 1/2. So P of A times 1/2 plus P of B times, same argument for B, we had 2 edges going to C, so that's 2/3. So P of C given B is 2/3, and C prime given B is 2/3. Multiply that by P of B. So if we had P of A over 2 plus P of B times 2/3, would that make sense?
Yeah, so it doesn't depend on P of B at all?
So the only additional step I did was I said we know that P of C and P of B have to be equal to each other because of symmetry. So I just added that in right away. That's all I did. Okay, other questions? This makes sense as an approach. So if we want to get useful probabilities in sort of like the long run, and we want to sort of basically walk around in a graph in order to compute those probabilities, we could use an approach kind of like this, and we're going to call that Markov chain Monte Carlo. So this is a Markov chain. It says that there are some states. The states here are cities, and we can transition from one state to another. So that's called a Markov chain. We'll get into Markov chains a bit more in the next lecture. But MCMC, Markov chain Monte Carlo, is a family of randomized algorithms for approximating something that is of interest to us, some quantity of interest, over a very large state space. And there's two pieces. The first piece is the Markov chain, which we just covered. This is the idea of sort of walking around randomly in a graph, where each state is conditioned on the previous state. We'll get into sort of what would those states look like in our Bayes nets in a second. And then there's this other piece, which is Monte Carlo, which is a city. It's a very expensive city in Monaco with a very famous casino, and it looks like this. Okay, so that's it. Markov chain Monte Carlo. Actually, no, that's not the Monte Carlo that we mean. So this is actually, Monte Carlo in the context of algorithms is usually based on sampling, and it's an algorithm that has some probability of producing an incorrect answer. And we're just going to hope that that probability goes to 0 as we get more and more time. So MCMC, the idea is basically we're going to wander around a bit. You know, I wake up in a city, I go to another city, and then we're just going to average what we see over time. We're going to look at a particular kind of Markov chain Monte Carlo algorithm called Gibbs sampling, which is named after a statistical physicist named Gibbs. And the idea here is we have to decide what are going to be the states in this Markov chain. And the states are just going to be complete assignments to all the variables. So imagine that we've like already sampled all the variables in our Bayes net, right? This is very similar to the idea of like simulated annealing. So when we were doing hill climbing, there was this idea that, you know, if we go up the hill, if we get a better evaluation for our subsequent state, we keep the sample. If we don't, there's like some probability that we still keep the sample anyway. It's kind of like that. It's not exactly the same. But states are complete assignments to all the variables. The evidence variables will remain fixed throughout the whole process of Gibbs sampling, and all the other state variables will eventually change. So to generate the next state, we have to have these sort of like transition dynamics in this Markov chain. So the next state, we're just going to pick a variable, any of the variables that are not evidence variables, and we're going to sample from that variable conditioned on all the other variables. Okay? So over time, this is going to tend to go towards areas of high probability, but it can go down too, sort of like simulated annealing. So we condition xi prime on the distribution, or we sample it from the distribution conditioned on all of the other variables. And you might think, okay, well that might be a lot of variables. Like, I'm getting nervous here. Like, we have this giant thing. I think, you know, the whole point of Bayes nets was that we don't have to do this. Oh wait, we do still have a Bayes net, so we can break this up. And it turns out that if you just condition on what's called a Markov blanket around that state, then that's a sufficient statistic for predicting this particular distribution. So you can again, Bayes nets to the rescue. We can concisely represent lots of different useful distributions with Bayes nets. And it turns out that Gibbs sampling is consistent with like this little asterisk and fine print that I'm sure you can't read from there. But the conditions are essentially that we have like well-behaved distributions. Okay, but what is this Markov blanket thing? Well, the Markov blanket looks like this. It says, for a particular x that I want to sample from, that's some node in my Bayes net, I want to draw a circle around that. And specifically, I want to draw a circle that includes both of x's parents, or any other parents that it might have, and it includes all of x's children, and it includes any parents of those children besides x as well. So there's three things to think about. One is the parents of x, that's the u variables. One is the children of x, those are the y variables. And then one are the sort of like aunts and uncles, the sort of like co-parents, if you will, like the other z's on the same line as x that are other parents of the y's, right? And so this whole thing is called the Markov blanket. And it turns out that you can sample from this joint distribution by sampling from this conditional distribution. Sorry, this is not a joint distribution. This is the conditional distribution conditioned on all the variables. You can simplify that to just condition on the Markov blanket, and you'll be good to go. Okay, so the process for Gibbs sampling says we're going to first sample a particular variable, which xi is like we can just choose between all the different variables. And then for each random variable that we pick, we're going to sample it again from this conditional distribution conditioned on the Markov blanket. Okay. So why can we do this? Well, this is proportional to the probability of x conditioned on its parents times the probability of y conditioned on the parents of y, and that's why you have to include these z's. Okay, so there's conditional probability tables. We'll multiply them together. It's sort of like the classic Bayes-Net thing. But the advantage of doing it this way is that we can have evidence that is distributed all throughout the Bayes-Net. It could be at any of these blue nodes. And over time, the evidence is going to sort of work its way through the rest of the Bayes-Net. And so after one step, we influence these nodes. And after 2 steps, we influence these nodes. And after 3 steps, we influence all the rest of the nodes for this network. And eventually, the whole distribution sort of reflects the true posterior distribution having conditioned on that particular evidence. So if we were to go back to our insurance example, which we know and love, remember likelihood weighting was this thing, is the blue line. It was better than rejection sampling because we weren't throwing stuff away. Gibbs sampling is this green line. And you can see that, like, okay, it starts out a little noisy because it's kind of like simulated annealing with a high temperature. But eventually, like, we get down to settling in a region that's pretty close to the same error rate as likelihood weighting. And that's like, okay, this is like, we could be slightly optimistic about this, but it doesn't look too amazing because there's like kind of high variance at the beginning. But it turns out that this example was like constructed for likelihood weighting to be great. And the reason for that is that all of the evidence variables are towards the top of the network, and so they all kind of trickle down through the network until we get to our query variable. If we were to instead query the age variable, and we needed all that evidence to trickle up the network, likelihood sampling would be pretty poor performance. I can't remember which side the slides are on. Yeah, so the blue line like doesn't converge after 1 million samples, whereas Gibbs sampling converges rather quickly. So this is like a situation where likelihood sampling, or likelihood weighting, or importance sampling is not going to get you to the right value quickly because you're going to be weighting your samples according to how well they reflect the evidence, and you're just going to get unlucky when that happens. And one of the samples is going to account for way too much of the samples that you've seen. So you'll give it a high weight, and you won't be so lucky on other samples, and so the things will sort of like not quite average out the right way. But Gibbs sampling doesn't have this problem because the evidence can filter through the whole network and everybody's happy. All right, so here's an example of Gibbs sampling. Step 1, fix the evidence. So if this is our evidence, rainy is true, then we have our Bayes-Net. It's this cloudy, sprinkler, rainy, wet grass thing. We fix the evidence, and then we initialize all the other variables randomly. It could be arbitrarily. Okay, so just pick some values for those random variables. Step 3, repeat the following. Choose a non-evidence variable, some x. Resample x from this conditional distribution where x is conditioned on its Markov blanket. And that looks like this. We pick s as our first variable that we're going to resample. So we pick s, and then we resample s conditioned on its Markov blanket, and that looks like this. So s conditioned on c, r, and not w. That gives us another sample. Maybe it's true. Then we pick another random variable, c, and we do the same thing. We're just repeating. So choose a non-evidence variable. C is a non-evidence variable. We resample C from its Markov blanket. So notice the Markov blanket for S includes its parents, C, its children, W, and all the other parents of its children, including R. So that's why we have to include this whole thing. But in this case, if we want to resample C, we need to include its parents. Well, it has no parents. We need to include its children, okay, S and R. And we need to include its children's other parents, which they don't have any other parents. So the distribution looks rather simple now. We have P of C conditioned on S and R. Okay, so we sample C, And the process repeats. We pick another non-evidence variable. Maybe we pick W this time. Now for W, we need to condition on its Markov blanket. Its Markov blanket is going to be parents. Okay, that's going to be S and R. It's going to be children of W. Oh, well, it doesn't have any children. And then all the other parents of its children, which it has no children. So this is W conditioned on S and R again. So we sample W, maybe we get a false. Okay? So this is the procedure of Gibbs sampling. That's the whole thing. And this repeats. So we just keep going. Yes, question. Where's the question?
Sorry.
Yeah.
My question was just about like when you say sampling from a conditional distribution, are you using like rejection sampling or likelihood of deviation?
So we are sampling from,
Like for example, when you resample C
yeah.
from like given S and R to be true, like how do you do that?
Yeah, okay, that's a good question. So how do you do this sampling when you're doing the sampling based on conditioning on the Markov blanket? So you have to figure out what the probabilities are for the variable you're sampling conditioned on the other variables in the Markov blanket. And so that's what this slide is about. So let's say that we are trying to figure out how to sample S conditioned on this evidence. So we need a conditional probability table for S conditioned on all the other three things. That's not a conditional probability table that we have in our Bayes net. It's right, like this conditional distribution is S given C. This one is W given S and R. And like, where do we get S given C, W, and R? And so the way we get that is like this, right? So the first thing that we do is we say conditional probability says that the probability of S conditioned on C, R, W is proportional to S, C, R, W's joint distribution. And this is the proportionality constant. Okay? The next thing that we do is we write the denominator in terms of the joint distribution. So we have to unmarginalize this S variable. So introducing this summation. Then once we have these two joint distributions, we can go back to our Bayes net structure and we factorize into these conditional probability tables. Those are the ones that we do have in the Bayes net. That's here. And then we move down to the next one. This says move summation term out. So these terms that are inside of the summation, we move them out of the summation, right? P of C and P of R given C, because those don't depend on S. So we pull them out. And then what we notice is that we can cancel out terms, right? So we have this term here, P of C. We can cancel that with P of C. We have P of R given C. We can cancel that out. And so what's left is the stuff on the bottom. And this is how you would compute P of S given its Markov blanket, given stuff in the Bayes net that we already know. Does that answer your question?
Yeah. And in this case, it would just be efficient because like when we're like modeling our Bayes net, we want the graph to be relatively sparse.
Yeah, the hope is that if you're using the Bayes net, then it's not going to have that many parents. It's not going to have that many children. The children aren't going to have that many parents. And so all this Markov blanket stuff can happen pretty quickly. Yeah, that's the hope. So many things are going to cancel out. Only the conditional probability tables with S in them remain. And more generally, only the CPTs that have the resampled variable need to be considered and joined together. So we might have to finish this up next class, but basically the idea is this is like the most largely used method in big Bayes nets. Here are some example libraries that you can use to do that. It can be compiled to run very fast if you can come up with like a Markov chain structure and you sort of figure out what these conditional Markov blanket probability tables are in advance. You can bake them into a graph like this, and then instead of looking at conditional tables, you just like run through this graph the same way we like woke up in a city and went to another city. You can compute the sort of like long-term probabilities really quickly. You can run it asynchronously, and people start thinking like, people have been suggesting that the brain actually does some version of this. So there are theories out there that in cognitive science that the brain's doing this. So yeah, we'll say a little bit more on this next time, and then we'll get into Markov models. See you then.